Good morning, everyone. I am Cellulose from Busan National University Department of Material Science and Engineering. And I'm so glad to be here to share my research direction for the cellulose decomposition by using the bifunctional group stopped carbon acid catalyst. As well known that the biomass energy is one of the renewable energy, and in recent years it has attracted increasing attention in the research area. And the energy demand from the biomass will be increased from 60% to 30% in Korea around 8 years later. So increasing the efficiency by using a solid catalyst for the cellulose component is very meaningful. We all know that the biomass is composed of lignin, cellulose, and hemicellulose mainly, and the cellulose is one of the good resources to get some biofuel and some value-added biochemicals. But we all know that the cellulose, the structure is very rigid due to the enormous amount of the hydrogen bonds and the glucose unite between the glucose monomers. So how to develop an efficient catalyst to increase the hydrolysis of cellulose to the reducing sugar unite is very difficult for the further upgrading. Always there are some process from the cellulosic biomass to the biofuel, from pre-treatment, hydrolysis, fermentation, and further hydrogenation. And in this work, we focus on the hydrolysis of cellulose to glucose. In the typical carbon acid catalyst, the functional groups of the COOH, OH, and SO3H are the typical site. So many researchers has been try to use many processes to dock this active site on the carbon and to increase the performance. Among them, the sulfonic acid group plays the role at the catalytic site, and the function of the COOH and OH group are also very important because they serve as the bonding site to improve the interaction between the cellulose and the catalyst. However, in this work, we try to increase the bonding function of the carbon acid catalyst by adding some novel groups by using the halogen groups of the fluorine and the chlorine. And we all know that the fluorine and the chlorine is strongly the electronegative. It could not only improve the interaction but also can increase acidity of the neighborhood SO3H group. In this work, we using the plasma technology for the synthesis of the halogen group supported carbon acid catalyst. First, with preparation of the carbon supported by using the solution plasma process by using the aromatic precursors with the fluorine and the chlorine active element. This solution plasma technology is also room temperature. Even the actual temperature of the plasma discharge is very high, but in the solution plasma, the temperature is below 40 degrees after 30 minute discharge. And after the carbon support synthesis, we using the gas-liquid interfacial plasma for the sulfonation to add the sulfonic acid group on the carbon acid support. And it is noted that this sulfonation process is performed under dilute sulfuric acid solution. In the typical sulfonation process, always the concentrated sulfuric acid was used, 90%, 90% or 98%. But in this work, we're using the 1 mole per liter sulfuric acid as the solvent. And this process is also high efficiency because it can be finished within 30 minutes. Both of these plasma technology, the solution plasma technology and the gas liquid interfacial plasma technology are all conducted under the room temperature. And this is the SEM analysis of the carbon obtained from the plasma technology. By using the similar aromatic precursors, we only change the active element from no any halogen group and Cl and F. We can see that the carbon shows similar morphology of the nanosphere size. It's around 10 to 50 nanometer. And the TEM analysis also shows the similar structure of the carbon we obtained. From the XRD and the BET, we get the crystalline structure and the texture property of this carbon. From the XRD, we can see that it shows the combined graphite-like and amorphous carbon. Because we use the some tungsten and graphite electrode, it also shows some composite of the graphite-like and amorphous carbon. And from the BET analysis, we see that the surface area is almost between 80 to 150 millimeter per gram, and the pore size is about 5 to 20 nanometer. We use the FTIR to check the chemical findings on the carbon before and after sulfonation. Before sulfonation, different with the toluene as the precursor, the Cl doped and F doped carbons all shows the corresponding chemical bondings on the carbon of the carbon Cl and the carbon F. And after the sulfonation, we also can see some the oxidation of the carbon of the OH intensity increasing and the OH and the carbon double oxygen bond and the SO double oxygen bond. It means the successful sulfonation of the carbon by using the gas liquid interfacial plasma technology. And we also use the XPS to certify the FTIR analysis. Compared to the toluene as the carbon precursor, we can see the doping of the chlorine and the fluorine on the Cl and F doped carbon. And this is the catalytic performance by using the sulfonated carbons for the cellulose hydrolysis. We have tried different temperatures from 100 degree to 140 degree. It shows that with increasing of the temperature, the catalytic performance increased. And compared to the without chlorine and the fluorine, the performance also gets improved. And compared to the chlorine and fluorine, the fluorine also shows higher performance compared to the chlorine group doping catalyst. And the solid acid property is very important for the heterogeneous catalysis. Therefore, we have to try by remove the catalyst after 6 hours reaction and only keep the solution reaction keep going. And without the catalyst, the conversion rate shows slight improve. It is because the slight leaching of some acid groups, but we also can see that the leaching is not very serious under the temperature of 140 degrees. In the summary, this work has developed a kind of novel carbon acid catalyst for the cellulose hydrolysis, and we have tried the halogen groups as the active site in the carbon catalyst for the cellulose hydrolysis. Actually, for the compared to the typical concentrated sulfonation process, this process is still not can be complete conversion of the cellulose. It is because even the gas-liquid plasma interfacial sulfonation process conducted in the dilute sulfuric acid, but compared to the concentrated sulfonation process, the active site amount is still not very enough. But this is a good foundation for using the plasma technology to do the surface functionalization. Thanks for your kind attention.
Thank you very much for your presentation. And is there any question or suggestion, opinion?
Thank you for the nice talk. Is there a way to characterize the density or concentration of F and Cl in your nanoparticles? So I was wondering whether the density of fluorine or chloride is similar within your two samples.
Actually, until now, the element of the chlorine and fluorine about the amount we only check by using the XPS, the surface checking. But we are trying to find a good method to improve the because the surface checking is not very actual for the real acid density. So we didn't show the actual amount of the fluorine and chlorine, but from the XPS analysis is about 4 to 5 millimole per gram.
Okay.
Any other question? Similar to those, like a previous question, I have also one question. Like, so is it possible to have like a different morphology or surface area depend on your precursor when you make the release?
There are two methods to change the morphology. One is we can use the template in the solution. It can change the carbon morphology we obtained. Another is we change to another kind of precursor, like the pyridine, the end of the 5 rings, not the 6 rings, 6 carbon rings. It also can change the carbon morphology, but we have compound toluene and even some other, like the the benzene. It all shows the carbon nanosphere.
So have you ever checked the actual surface area of your catalyst?
Surface area? Oh yeah, we have checked.
Sorry, I've made this.
The surface area is around 100 square meter per gram, and after sulfonation it shows decrease because the acid group doping makes the aggregation of the carbon sphere.
How about the durability of your catalyst? Look like the reaction is so very difficult.
The reaction?
I mean the durability or like cyclability of your catalyst.
It also shows the slight decrease of the performance, but this is because some leaching of the acid group in the aqueous phase.
Thank you very much. And any other question? 없으면 thank you for your nice presentation. Thank you.